Hey, good morning. Limits, chapter 2.2. We discussed what a limit was. And here it is. A limit of f of x as x approaches c is L. And what we said, more informally, this is the formal definition of a limit. What we said more informally was, as x gets really, really close to c, the function gets really, really close to this y value L. Maybe sometimes they use as x gets arbitrarily close to c. The function gets arbitrarily close to L. The picture's here. As x gets close to c, really, really close to c, the function gets really, really close to L. And it may exist, it may be colored in there, or maybe not colored in there. I kind of did both. But as x gets close to c, the function gets close to L. So that's a very informal way of talking, and mathematics is a formal language. So the formal definition of a limit says the same thing, or it formalizes what we just said. And I'd like to help you read this. So it says, let f be defined on an open interval containing c. So that's some open interval, the function has to be defined. And some open interval containing c. It doesn't have to be defined at c. That's where that hole comes in, Sometimes it doesn't have to be defined at c. And then L is a real number. And so the phrase, the limit as x approaches c of the function f of x equals L, means this. And here's what the formal definition of this limit is. That for each epsilon greater than 0, that's a little Greek letter epsilon, and it's for each epsilon greater than 0, so it's just you can pick any number that's greater than 0. And since the point of that is you can pick any number greater than 0, so what if you pick a smaller number? What if you pick a smaller number? For each teeny little number you might pick that's greater than 0, there exists another little number greater than 0, another small number, delta. That's this Greek letter delta, such that that the absolute value of x minus c is less than delta, then the absolute value of the function minus L is less than epsilon. This is an absolute value inequality, which is like a distance. I don't know if you remember, we used to do this absolute value inequality. Let me just try this. X minus c is less than delta. Back in intermediate algebra, you learned how to solve a less than absolute value inequality. I would make a sandwich here between delta and negative delta, and then I'd add c. This is how I solve an absolute value inequality. So then x is left in the middle. It's delta plus c. Hang on. What did I do? I just added a c plus delta, and I'm adding a c over here, c minus delta. And x lives in between there. X is between c plus delta and c minus delta. So that's, I don't know, a shorthand way of saying that. When x gets really, really close to c, how close to c? Within delta. What's delta? Some teeny little number. So if x is really, really close to c, within delta of c, so over here is c plus delta, over here is c minus delta, x is within there, it's getting real close to c, then the same idea. The function is really close to L. How close to L? Less than epsilon. And what's epsilon? Some teeny little number. How teeny? As teeny as you want to make it. If it's not teeny enough, make it teenier. This is the formal definition of what it means to get really close. Here's the picture. Again, the function is getting really close to L. It's within epsilon of L. Within an epsilon distance of L. Whether this exists or not. Whether there's a hole there or not. It's within that. And you can make this smaller. You can make all this smaller. Delta and epsilon are designed to be very small little quantities. So that's weird. That's tricky. That's how math talks. When you major in math, everything's a formal. It's a formal language, and everything is formally defined and formally proven. I teach some of my calculus. I teach like that. Some calculus I don't teach like that. I don't prove everything. But they do when you take advanced calculus. Like I said, when you major in math, you learn to talk like this quite a bit. So anyway, good luck.